Okay, I think it's working. Hopefully it is, because if it isn't, I'll cry. Okay, so, derivatives. Pretty wild. So, first thing I'll do is, I think you guys have just started derivatives, so like, you're not really gonna be all that far into it, but definition, derivative, and stuff you should be doing. So, difference between a tangent and a secant line, right? So this is my function, f of x, right? I should actually make this like curvier so I can better illustrate my point. Yeah. So if I have f of x, right? If I want to make a secant line is just a line that crosses my function at 2 points. I can make a secant line of this function in multiple different places. I just pick 2 points on the function, and I make a line that goes through them. That did not go through that point. Pretend it did, right? And so then you can make these points go like closer and closer together, right? Like this. And so at some point, those points are going to get so close together that they'll be the same point. And when that happens, we don't call it secant, we call it a tangent line. And essentially, all a derivative is at the point, like whatever point this is, let's call this point A. At point A, this tangent line that I drew in green, all the derivative is the derivative of f of x at point A is just the slope of that tangent line, that green line that I drew. Right? Okay. So, if that makes sense, we'll see how definition of derivative comes into it. So, definition derivative, is actually pretty simple. Oh my god. If you think about it. So, if I have a graph like this, right? And I'll just do the same-ish function.
Your arrows still suck.
Oh my god, leave me alone. And let's say I have the point x, then I have the point x plus h. So then this is going to be f of x, and then this is going to be f of x plus h, because I just call those 2 points, right? And so then the distance between this is h, right? Because x plus h, x, does that make sense to you, Nanya? Okay, yeah, right? So all the derivative is just a slope. The derivative is slope. Think of it as slope. So slope is going to be rise over run. So from that, I can extrapolate that it's going to be f of x plus h minus f of x over h, sorry, because this is h, right? And then my distance here that I need to find is going to be f of x plus h minus f of x, whatever that is. That makes sense. And then the way we get the limit from that is that as the thing is, as the limit of h goes to 0, right? So this is x plus h. So as h gets smaller and smaller and smaller, as h goes to 0, it's just going to go to x, meaning that at x the slope is going to be like this. That's going to be my derivative of x, which is what we're trying to find. So as limit as h goes to 0, f of x plus h minus f of x over h, my h over here is just, not that, my h over here is going to get smaller and smaller and smaller until it approaches 0, meaning my point is just going to be at x, meaning I'll just find the derivative of x, which is what I want to find. Does that make sense? X plus c is just kind of like, as x goes to c is kind of a different way of rewriting the same thing. So I'm going to like skip over that. Okay. And then, so non-differentiability. So first of all, derivative is slope, right? So if I have a curve like this, over here, my derivative at this point, let's call it b, is going to be 0 because it's a horizontal line, and slopes of horizontal lines are 0. Now on the other hand, if I have this line like x equals 3, the derivative of this line is not going to exist because there's no slope of a vertical line. Okay, and then the two other differentiable things, non-differentiable things are cusps and corners, right? Okay, so the reason, oh my god, shoot, I screwed up. That didn't happen. Shh, you said nothing. So the reason cusps and corners aren't differentiable, so like say I have the absolute value function, right? So first you gotta think about like continuity. So if something is not continuous, it will not be differentiable, right? And so, the thing, this is a little hard to explain, but basically, like, that's not the right color. If you look at it from this section, the right hand and the left hand side, my derivative at this point, let's say it's going to be like this, right? My derivative at this point is going to be like this. At this, it's going to be this. Here, it's going to be this. Here, it's going to be here. Here, it's going to be here. At no point do these ever converge to like the same thing. Because over here, when I have a curve, what happens is like a gradual, like they gradually reach the same point over here. Right? But here, they don't do that. They never really converge to the same thing. So the derivative does not exist. And if I have a cusp, what does a cusp look like again? It's like this, right?
Sure.
What is that on the cusp?
No, that probably is a cusp. I just have no idea what a cusp is. Cusp, oopsie, in math. Yeah, it's like that.
Okay, yeah, so that's right. An example of a graph of a cusp, x to the 2/3, if you graph that, that'll be a cusp. Yeah, it's kind of the same thing. So, like, I can have my derivative right here be like this, my derivative right here be like this, my derivative right here be like this, and they're never gonna match. So the derivative can't exist.